Now, in this lecture, we find out the radius of the circle using two different methods. In the drawing, we have triangle ABC. Triangle ABC blocks the circle, or the circle is inscribed by triangle ABC. In addition, we know that this angle ABC equals to 60 degrees in its size, and this angle ACB equals to 75 degrees. In addition, we also know that side BC of this triangle ABC equals to 2 units in its length. And our mission is to find out the radius of this circle that is inscribed by this triangle ABC. We start with the first method, and the first method, for point C, we draw perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and on AB as D. Here we created the right triangle BDC. So I copied the right triangle BDC in the new page, and we'll analyze this right triangle BDC. So actually, this is the right triangle BDC that I copied from the original drawing. Side BC equals to 2 units according to what is given as the equation. And we also know that angle DBC equals to 60 degrees in its size. In this triangle BDC, cosine 60 degrees equals to BD over BC. With again cosine 60 degrees equals to BD over BC. So cosine 60 degrees equals to BD over BC, and BC is 2. Cosine 60 degrees is 1/2. So we substitute cosine 60 degrees by 1/2. So 1/2 equals to BD over 2. Here we multiply this equation by 2. And we get that BD equals to 1 unit in its length. BD equals to 1 unit in its length. Here, this line segment BD is equals to 1 unit in its length. We continue to focus on the right triangle BDC. Here, sinus 60 degrees equals to DC over BC. Repeat again, sinus 60 degrees equals to DC over BC. So it is DC over BC, and BC is 2. Sinus 60 degrees is square root of 3 over 2, so square root of 3 over 2 equals to DC over 2. Here we multiply this equation by 2, and we get that DC equals to the square root of 3 units in its length. DC equals to the square root of 3 units in its length. Here, this line segment DC this line segment DC equals to the square root of 3 units in its length. In the right angle BDC, this is the right angle, this is equals to 90 degrees in its side, this angle equals to 60 degrees. 90 degrees plus 60 degrees, it is 150 degrees. So the missing angle here must be equal to 30 degrees in order to complete the sum of the angles in this right angle BDC to 180 degrees. The missing angle here must be equal to 30 degrees. It is given us the equation that the big angle ACB equals to 75 degrees. Angle DCB equals to 30 degrees. Therefore, the missing angle here angle ACB, angle ACD equals to the big angle that is 75 degrees minus this angle that is 30 degrees, so 75 degrees minus 30 degrees equals to the missing angle ACD. So the missing angle ACD equals to 45 degrees in its size. In the next step, we'll focus on the right triangle ADC. So I copy the right triangle ADC in the new page and we'll analyze this right triangle ADC. So actually this is the right triangle ADC that I copied from the original drawing. Angle ACD equals to 45 degrees. Side DC equals to the square root of 3 units in its length. So in the right triangle ADC, the sum of the angles must be equal to 180 degrees. So 45 degrees plus 90 degrees is 135 degrees. Therefore, this missing angle must be equal to 45 degrees in its size. Again, in order to complete the sum of the angles in this right triangle ADC to 180 degrees, the missing angle must be equal to 45 degrees in its size. So, those two angles, they are equal to each other. And we have the rule that in front of equal angles in the triangle, there are equal sides. So those two sides that are located in front of those two equal angles must be also equal to each other. That is to say, side AD must be equal to side DC. According to the rule that if front of equal angles in the triangle, they are equal sides. But we just right now found out that DC equals to the square root of 3 units. And for this equation, AD equals to DC equals to the square root of 3 units. We derive that side AD is also equals to the square root of 3 units in its length. AD equals to the square root of 3 units. So you can write down in the original drawing that side AD equals to the square root of 3 units in its length. In the next step, we continue to focus on the right triangle, triangle ADC. Here we will implement the Pythagoras theorem on this right triangle, triangle ADC. Here by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in the right triangle ADC, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AC, so AC squared equals to AD squared plus DC squared. AC squared, that is the square of the hypotenuse, equals to AD squared. AD is equal to 3, therefore AD squared is equal to 3 squared, that is 3, plus DC squared. DC is equal to 3, therefore DC squared is equal to 3 squared, that is 3. So in total, AC squared equals to 3 plus 3, that is 6. AC squared equals to 6. We take a out of this equation, and we get that AC equals to the square root of 6 units. AC equals to the square root of 6 units in its length. So this side AC equals to the square root of 6 units in its length. Okay, so in the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule number 15. According to rule number 15, the radius of a circle that is described by triangle ABC is equals to R. The radius R equals to the area of triangle ABC that blocks the circle over S. S is the semi-perimeter of the same triangle, triangle ABC. Here we have a circle that is described by triangle ABC, or triangle ABC blocks this circle. So the radius R of this circle, according to this rule, rule number 15, will be equal to the area of triangle ABC over the semi-perimeter of triangle ABC. Again, the semi-perimeter of triangle ABC equals to the perimeter over 2. The perimeter is AB plus BC plus AC. That is the sum of its side lengths. And if we divide the perimeter by 2, we get that it will be the semi-perimeter. So the radius of this circle that is inscribed by triangle ABC, the radius R equals to the area of triangle ABC over the semi-perimeter of the same triangle, triangle ABC. So we can actually implement rule number 15 in our drawing. Why? Because in our drawing we have a circle that is described by triangle ABC. Our mission is to find out the radius of the circle. So the radius of this circle, according to number 15, we define the radius of this circle as r. So the radius r of this circle that is described by triangle ABC will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. Okay, according to rule number 15 goes. So, what is the area of triangle ABC? The area of any triangle is equal to the base of the triangle times the height to the base over 2. All divided by the semi-perimeter of the same triangle, triangle ABC. So we choose the base of the triangle ABC as AB. So the base is AB times the height. The height must create 90 degrees with the base AB. CD creates 90 degrees with the base, therefore CD is the height. Again, so the base is AB times the height to the base is CD divided by 2. All divided by the same perimeter of the same triangle, triangle ABC. So it is AB. AB is square root of 3 plus 1. Times CD. CD is equal to 3 divided by 2, all divided by the semi-perimeter of the same triangle, triangle ABC. The semi-perimeter of this triangle, triangle ABC equals to the perimeter over 2. The perimeter of this triangle, triangle ABC is AB plus BC plus AC. AB plus BC plus AC. And if we divide the perimeter by 2, we get the semi-perimeter S. So the radius R that we are looking for of this circle that is described by triangle ABC equals to square root of 3 plus 1 times square root of 3 over 2 divided by the semi-perimeter that is AB plus BC plus AC over 2. Here the value of this expression is equal to, that is to say, the area of triangle ABC, that is the value of this expression, is 2.366 square units over AB. AB is equal to 3 plus 1 plus BC. BC equals to 2 units in its length according to what is given as the question. So BC is 2 plus AC. AC is square root of 6 units, all divided by 2. So it is 2.366, and this expression in total, that is the semi-perimeter of triangle ABC, is equals to 3.3 2.591. So the radius of the circle that we are looking for equals to 2.366 over 3.591. That is actually 0.6589 units. So the radius of the circle that we are looking for equals to 0.6589 units. Repeat again. The radius of this circle, the radius r of this circle, it is equals to 0.6589 units. So we finished with the first method. In the next step, I will present to you how to find out the radius of this circle according to the second method. We will define the center of this circle as O. We define the point of tendency of tangent AC with this circle as F. We define the point of tendency of tangent AB with this circle as E. And we define the point of tendency of tangent BC with this circle as D. We join points O and D together by a straight line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of this circle. We define the radius of this circle as R, so OD equals to R. And here we have rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here we have line segment AB is tangent to this circle at point M. Point M is the point of tendency. And you have the radius OM that is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule, rule number 1. We can actually implement rule number 1 in our drawing. Why? Because in our drawing we have the radius OD that is drawn to point D, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. If BC is perpendicular to DO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Likewise, we join points E and O together by a straight line. EO is the radius of the circle, is equals to r. Again, we have the radius EO that is known to point E, that is the point of tendency of tangent AB with this circle. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points F and O together by a straight line. Again, OF is the radius of this circle that is equals to R. The radius OF is known to point F, that is the point of tendency of tangent AC with this circle, and therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle also equals to 90 degrees. Here we have also rule number 2. According to rule number 2, the lengths of two tangents from a common standpoint to a circle are equal. We have a circle and the common standpoint, point P. From the common standpoint, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule number 2, they are equal to each other. That is to say, PA equals to PB. We can actually implement rule number 1 in our drawing. Why? Because in our drawing, if you focus on the common standpoint, point C, from the common standpoint, point C, we have two tangents to this circle, tangent CF and tangent CD. And according to rule number 1, they are equal to each other. That is to say, CF equals to CD. So we can note here that CF equals to CD according to rule number 2. Likewise, we focus on the common standpoint, point B. From the common standpoint, point B, we have two tangents to this circle, tangent BE and tangent BD. And according to rule number 2, they are equal to each other. That is to say, BE equals to BD. So we can write down here that line segment BE equals to line segment BD according to the same rule, rule number 2. In the next step, we join points O and B together by a straight line. And we join points O and C together by a straight line. And we will prove that the green triangle EOB, the green right triangle EOB, is congruent to the yellow triangle ODB. Okay, again, we prove that the green triangle is congruent to the yellow triangle. So I write it down. We prove that the green triangle EOB is congruent to the yellow triangle BOD. So write those two triangles congruent to each other. First of all, EO, side EO of the red triangle equals to side OD of the yellow triangle. They are both the radii of the circle, therefore they are equal to each other. So I can write down that side EO of the red triangle equals to side OD of the yellow triangle. They are both the radii of the circle, therefore they are equal to each other. In addition, BE equals to BE. BE equals to BD. Side BE of the green triangle equals to side BD of the yellow triangle. Here, BE equals to BD according to rule number 2. Repeat again. Side BE of the green triangle equals to side BD of the yellow triangle according to rule number 2. And finally, side OB is a common side that belongs to both triangles, so we can write down that OB equals to itself as a common side that belongs to both triangles. OB equals to OB. Repeat again. Side OB equals to itself as a common side that belongs to both triangles. So if we proved that all the three sides of the green right triangle BEO are corresponding equal to all the three sides of the yellow triangle, triangle BOD. Therefore, we proved that the green triangle BEO is congruent to the yellow triangle BOD according to side rule. So I write it down. We proved actually that the green right triangle EOB is congruent. This is the sign of congruent to the green to the yellow right triangle, triangle BOD. They are congruent to each other according to side rule. And from the fact that those two triangles can go to each other, we will derive that those two angles must be also equal to each other. So this is angle EBO, and this equals to this angle that is actually angle OBD in the yellow triangle. Repeat again. From the fact that the two triangles can go into each other, we will derive that angle EBO in the green triangle equals to angle OBD in the yellow triangle, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So if we define one of those angles is theta, then the other angle must be also equal to theta because they are equal to each other. Okay. So theta plus theta equals to 60 degrees according to what is given as the question. 2 theta equals to 60 degrees. We divide this equation by 2. And finally we get that angle theta equals to 60 degrees over 2 is 30 degrees. So hopefully this is angle theta is equals to 30 degrees in its size. In the next step, we'll focus on the right yellow triangle BOD, so I'll copy this right yellow triangle in the new page and we'll analyze this right yellow triangle BOD. OD equals to R, this is the radius of the circle, and this angle OBD equals to 30 degrees. So actually, this is the right yellow triangle OBD that I copied from the original drawing. In this right triangle OBD, tangents 30 degrees equals to OD over BD. Again, tangents 30 degrees equals to OD over BD. OD is R, is the radius of the circle, so it is R over BD. So tangents 30 degrees equals to R over BD. Here we multiply this equation by BD and we get that BD times tangents 30 degrees equals to R. Here we divide this equation by tangents 30 degrees. And we get that the radius R of this circle, the radius that we are looking for, equals to actually BD equals to R over tangents 30 degrees. Okay, we just divided this equation by tangents 30 degrees and found out that BD equals to R over tangents 30 degrees. So we can write down here that this line segment BD it is equals to R over tangents 30 degrees. Likewise, we repeat on the same process on those two triangles. So we prove that the orange right triangle ODC is congruent to the pink right triangle FOC. So we'll prove that the orange triangle ODC is congruent to the pink right triangle OFC. So why those two triangles congruent to each other? First of all, side OF of the pink triangle equals to side OD of the orange triangle. They are both the radii of the circle, therefore they are equal to each other. Repeat again. Side OF in the pink triangle equals to side OD in the orange triangle. They are both the radii of the circle, therefore they are equal to each other. They are equal to R, the radius of the circle that you are looking for. In addition, CF equals to CD according to rule number 2. Here, CF equals to CD according to rule number 2. Side CF in the pink triangle equals to side CD in the orange triangle according to rule number 2. CF equals to CD according to rule number 2. And finally, side OC is a common side that belongs to both triangles, so we can write down that OC equals to itself. It's a common side that belongs to both triangles. And again, side OC equals to itself as a common side that belongs to both triangles. So we actually prove that all the three sides of the pink triangle OFC are correspondingly equal to all the three sides of the orange triangle CDO. Therefore, we actually proved that those two right triangles can go to each other according to side rule. So I write it down, triangle ODC is congruent to triangle OFC according to side rule. And from the fact that those two triangles can go to each other, we will derive that those two angles are also equal to each other. So this is angle OFS CFO in the pink triangle, FCO, angle FCO in the pink triangle is equals to angle OCD in the orange triangle. It again, angle FCO in the pink triangle equals to angle DCO in the orange triangle according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore those two corresponding angles must be also equal to each other. So if we define one of those angles as alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha equals to 75 degrees according to what is given as the equation. That is to say 2 alpha equals to 75 degrees. We divide this equation by 2. And finally we get that alpha equals to 75 over 2 is 37.5 degrees. So this angle alpha equals to 37.5 degrees. In the next step, I will copy the right triangle ODC, the right orange triangle ODC in a new page, and we will analyze this right triangle ODC. Side OD is the radius of this circle that is equals to R. And this is angle alpha that is equals to 37.5 degrees. So actually this is the right triangle ODC that I copied from the original drawing. In this right triangle ODC, tangents 37.5 degrees equals to OD over DC. So tangents 37.5 degrees equals to OD, that is R, over DC. Repeat again. Actually found out that in the right triangle ODC, tangents 37.5 degrees equals to R over DC. Here we will multiply this equation by DC, and we get that DC times tangents 37.5 degrees equals to R. Here we divide this equation by tangents 37.5 degrees. And we get that DC equals to R over tangents 37.5 degrees. So this line segment DC equals to R over tangent 37.5 degrees. So I write it down in this drawing that this line segment DC equals to R over tangent 37.5 degrees. Side BC, from the drawing it is very easy to see that side BC equals to BD plus DC again. BC equals to BD plus DC. This is again BC equals to BD plus DC. BC equals to 2 units its length, so we substitute BC by 2. So 2 equals to BD plus DC. BD is R over tangent 30 degrees, so we substitute BD by R over tangent 30 degrees. Again, BC is 2, so we substitute BC by 2. BD is R over tangent 30 degrees, so we substitute BD by R over tangent 30 degrees, plus DC. DC is R over tangent 37.5 degrees, so we substitute DC by R over tangent 37.5 degrees. So we actually found out that 2 equals to R over tangent 30 degrees plus R over tangent 37.5 degrees. So 2 equals to, here we take R a second factor out of those two expressions. So inside the brackets, for this expression we left only with 1 over tangent 30 degrees. After we took R as a second factor for this expression, we left only with 1 over tangent 37.5 degrees. So 2 equals to R, and 1 over tangent 30 degrees equals to 1.732 plus 1 over tangent 37.5 degrees equals to 1.3032. So in conclusion, we found out that 2 equals to R, and 1.732 plus 1.3032 equals to 3.0352. So if we found out that 2 equals to R times 30352, here we will divide this equation by 30352, and we get that R, the radius that we are looking for, equals to 2 over 30352. 2 over 30352 equals to 0.6589 units. Okay, so we actually found out that the radius R of this circle equals to 0.6589 units. So in both methods, we actually found out that the radius of this circle R equals to 0.658 units. 0.6589 units. So in the next step, I'll summarize the lecture. We start with the first method, of course. In this lecture, we found out the radius of this circle that is inscribed by this triangle, triangle ABC. So triangle ABC blocks this circle. In the first method, we did a construction, that is to say, from point C, we draw perpendicular on AB. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C on AB as D. Here, by doing this construction, we get there the right angle, triangle CDB. So I copy the right angle CDB in a new page, and we analyze this right angle, triangle CDB. This is the right angle CDB that I copied from the original drawing. In this right angle CDB, cosine 60 degrees equals to dB over BC. So cosine 60 degrees equals to dB over BC, and BC is 2. So cosine 60 degrees equals to dB over 2. Cosine 60 degrees is 1/2, so 1/2 equals to BD over 2. 1/2 equals to BD over 2. We multiply this equation by 2, and finally found out that BD equals to 1 unit in its length. This line segment BD equals to 1 unit in its length. We continue to focus on the right triangle BDC. On the right triangle BDC, sinus 60 degrees equals to DC over BC. Again, sinus 60 degrees equals to DC over BC. That is to say, sinus 60 degrees equals to DC over BC, and BC is 2. So sinus 60 degrees equals to DC over 2. Sinus 60 degrees is square root of 3 over 2, so square root of 3 over 2 equals to DC over 2. We multiply this equation by 2, and finally found out that side DC equals to the square root of 3 units in its length. Here, this side DC equals to the square root of 3 units in its length. We continue to focus on the right triangle DBC. On the right triangle DBC, this angle equals to 60 degrees, this angle equals to 90 degrees. 60 degrees plus 90 degrees, it is 150 degrees. Therefore, the missing angle here must be equal to 30 degrees in its size in order to complete the sum of the angles in this right triangle DBC to 180 degrees. The missing angle here must be equal to 30 degrees in its size. So we know that angle DCB equals to 30 degrees. The big angle ACB equals to 75 degrees. So the big angle ACB minus this angle DCB, that is 30 degrees, must be equal to the missing angle ACD. This angle in ACD. So 75 degrees minus 30 degrees, it is equals to 45 degrees. So the missing angle here ACD equals to 45 degrees in its size. Then I copied the right triangle ACD in a new page and analyze this right triangle ACD. This is the right triangle ACD that I copied from the original drawing. We just right now found out that this angle ACD equals to 45 degrees in its size. So in the right triangle ACD, this angle equals to 90 degrees. This angle equals to 45 degrees. 90 degrees plus 45 degrees, it is equals to 135 degrees. So the missing angle here must be equal to 45 degrees in its size in order to complete the sum of the angles in this right triangle ADC to 180 degrees. The missing angle here must be equal to 45 degrees in its size. So those two angles are both equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle there are equal sides. So those two sides that are located in front of those two equal angles must be equal to each other. That is to say, side AD must be equal to side DC. AD equals to DC, but we found out that DC equals to the square root of 3 units. So DC equals to the square root of 3 units, and from this equation AD equals to DC equals to the square root of 3 units, we derive that side AD also equals to the square root of 3 units in its length. This side AD equals to the square root of 3 units in its length. We can write down that this is side AD is equals to the square root of 3 units in its length. Then we continue to focus on the right triangle, triangle ADC. Here we implemented the Pythagoras theorem on this right triangle, triangle ADC. According to the Pythagoras theorem, in the right triangle ADC, AC square equals to AD square plus DC square. So AC square, that is the square of the hypotenuse, equals to AD square. AD is square root of 3. Therefore, AD square is square root of 3 square, that is 3, plus DC square. DC is also square root of 3, so DC square is square root of 3 square, that is 3. So in total, AC square equals to 3 plus 3, that is 6. AC square equals to 6. We took a root out of this equation and finally found out that AC equals to the square root of 6 units. Here, this side AC equals to the square root of 6 units in its length. Then I presented to you the new rule and we implemented the new rule in our drawing. The new rule is rule number 15. According to rule number 15, the radius of a circle that is described by a triangle ABC could be any triangle, is equal to the radius R of the circle that is described by a triangle is equals to the area of the triangle that blocks the circle over the semi-perimeter of the same triangle ABC. So here we have a circle. This circle is described by this triangle ABC. So the radius of this circle, the radius R of this circle equals to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle ABC. The semi-perimeter of any triangle is the perimeter over 2. The perimeter is the sum of its side lengths, that is to say that is AB plus BC plus AC, and if we divide the perimeter by 2, we get the semi-perimeter S. So it is A plus B, AB plus BC plus AC over 2. It is equal to the semi-perimeter of this triangle ABC. So the radius of this circle, R, equals to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle ABC. We can implement rule number 15 in our drawing. Why? Because in our drawing we have a circle that is described by triangle ABC. Whenever you have a circle that is described by a triangle, you can implement rule number 15 in that circle. So here we can implement rule number 15. According to rule number 15, we get that the radius R of this circle, that is the radius that we are looking for, the radius R of this circle equals to the area of triangle ABC over the semi-perimeter of the same triangle ABC that blocks this circle. Again, the radius R of this circle that is described by triangle ABC is equals to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle ABC. The area of any triangle is the base of the triangle times the height to the base over 2 over the semi-perimeter of the same triangle ABC. We choose the base of this triangle ABC as AB, and the height to the base is CD. Why the height to the base is CD? Because it creates 90 degrees with the base AB. So the base is AB times the height to the base is DC. So the area of triangle ABC in total equals to the base AB times the height, that is DC, over 2, divided by the semi-perimeter of the same triangle ABC. We have already found out that the base AB in total equals to the square root of 3 plus 1. So here AB equals to the square root of 3 plus 1 times the height DC. DC equals to the square root of 3. So here DC or CD equals to the square root of 3 all divided by 2. And we have to divide it by the semi-perimeter of the same triangle ABC. The semi-perimeter of this triangle ABC equals to the perimeter, that is AB plus BC plus AC over 2. Again, the semi-perimeter of triangle ABC equals to the perimeter, that is AB plus BC plus AC divided by 2. This expression in total equals to 2.366, and it is divided by AB, that is square root of 3 plus 1, plus BC, that is 2, plus AC that is actually square root of 6 units. Here AC is square root of 6 units. Here AC is square root of 6 units. So it is AB that is square root of 3 plus 1, plus BC that is 2, plus AC that is square root of 6, all divided by 2. So this expression is the same perimeter of triangle ABC, and this expression in total equals to 3.591 units. So in conclusion, we found out that the radius R equals to 2.366 over 3.591. That's actually 0.6589 units. So actually found out that according to the first method, the radius R of this circle equals to 0.5689 units. We finished with the first method. Then I presented to you how to find out the radius of this circle according to the second method. In the second method, we defined the center of this circle as O. We define the point of tendency of tangent AB with this circle as E. We define the point of tendency of tangent AC with this circle as F. And we define the point of tendency of tangent BC with this circle as D. Then we join points O and D together by a straight line. Point O is the center of the circle, point D is the point of the circle center. For all this, the radius of this circle that we defined as R. The radius OD is drawn to point D, that is the point of tendency of tangent BC with this circle. That whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. If BC is perpendicular to DO, it means that this angle equals 90 degrees. This angle also equals to 90 degrees according to rule number 1. Then we join points O and D together by a straight line. O is the radius of this circle. This equals to R. The radius OE is drawn to point E, therefore according to rule number 1, this angle equals to 90 degrees and this angle equals to 90 degrees. Likewise, we join points O and F together by a straight line. OF is the radius of this circle, that is equal to R. The radius OF is drawn to point F, that is the point of tendency of tangent AC with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius FO, that is to say this angle equals to 90 degrees, this angle also equals to 90 degrees according to rule number 1. Then we focused on the common external point C. From the common external point C, we have two tangents to this circle, tangent CF and tangent CD. And according to rule number 2, they are equal to each other. That is to say, CF equals to CD according to rule number 2. Again, CF equals to CD according to rule number 2. Likewise, we focus on the common external point B. From the common external point B, we have two tangents to this circle, tangent BE and tangent BD. And according to rule number 2, they are equal to each other. Here, BE equals to BD according to rule number 2. Then we join points O and B together by a straight line, and we join points O and C together by a straight line. Here, we have we proved that the green triangle OEB is congruent to the yellow triangle OBD. So why those two triangles congruent to each other? First of all, those two sides now both the radii of the circle, therefore they are equal to each other. So EO equals to OD. Here, those two sides are also equal to each other according to rule number 2. That is to say, side B equals to side BD according to rule number 2. BE equals to BD according to rule number 2. And finally, side BO is a common side that belongs to both triangles. So BO equals to itself as a common side that belongs to both triangles. So I should prove that all the three angles of the right green triangle EOB are correspondingly equal to all the three angles of the yellow right triangle BOD. And therefore, those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other, according to the rule that corresponding angles and congruent triangles are equal to each other. Those two triangles can go into each other, therefore, those two corresponding angles must be also equal to each other. So if one of these angles is theta, then the other angle must be also equal to theta because they are equal to each other. Okay, so theta plus theta in total must be equal to 60 degrees. Here, theta plus theta, that is 2 theta equals to 60 degrees. We divided the equation by 2 and finally found out that angle theta equals to 30 degrees. So this is angle theta that is equals to 30 degrees in its size. Then I copied the yellow right triangle OBD in a new page and we analyze this right triangle OBD. This is the yellow right triangle OBD that I copied from the original drawing. This is angle theta that equals to 30 degrees. And side DO equals to R, it is the radius of the circle. So in the right triangle BOD, times 30 degrees equals to R over times 30 degrees equals to OD over BD. Times 30 degrees equals to OD over BD. OD is R, therefore times 30 degrees equals to OD that is R over BD. So times 30 degrees equals to R over BD. We multiply this equation by BD and found out that times 30 degrees equals to BD, that R equals to BD times 30 degrees. Again, BD times 30 degrees equals to R. After we multiply this equation by BD, we found out that BD times times 30 degrees equals to R. Then we divided this equation by times 30 degrees and finally found out that BD equals to R over times 30 degrees. Here BD equals to R over times 30 degrees. You can find down here. This line segment BD equals to R over times 30 degrees. We repeated on the same process on those two triangles. We actually proved that the orange triangle ODC is congruent to the pink triangle OFC according to side rule. Why those two right triangles congruent to each other? First of all, OF equals to OD, they are both the radii of the circle, therefore they are equal to each other. In addition, side FC equals to side CF equals to side CD according to rule number 2. Here CF equals to CD according to rule number 2. And finally we have side CO, that is a common side that belongs to both triangles, so CO equals to itself as a common side that belongs to both triangles. So we actually prove that the pink triangle OFC, all the three sides of the free triangle OFC, of the right triangle OFC, are correspondingly equal to all the three sides of the orange triangle ODC. Therefore, we actually proved that those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles and congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha equals to 75 degrees. That is to say 2 alpha equals to 75 degrees. We divided this equation by 2 and finally found out that alpha equals to 37.5 degrees. If this is angle alpha, that equals to 37.5 degrees. Then I copied the orange right triangle ODC in the new page and we analyze this right orange triangle ODC. This is the orange triangle ODC that I copied from the original drawing. This is angle alpha that equals to 37.5 degrees. Side OD equals to R, is the radius of the circle. So in this right triangle ODC times 37.5 degrees equals to OD over DC. Times 37.5 degrees equals to OD over DC. OD is R, so we substitute OD by R. We found out actually that times 37.5 degrees equals to R over DC. Here we multiply this equation by DC and we found out that R equals to DC times 37.5 degrees. Here we divided this equation by times 37.5 degrees and finally found out that DC equals to R over times 37.5 degrees. Here this line segment DC equals to R over times 37.5 degrees. So BC in total equals to BD plus DC. Again, BC equals to BD plus DC. BD plus DC equals to BC. So BC is 2, so we substitute BC by 2. BD is R over times 30 degrees, so we substitute BD by R over times 30 degrees. And here DC is R over times 37.5 degrees, so we substitute DC by R over times 35 degrees. So in conclusion, we found out that 2 equals to R over times 30 degrees plus R over times 37.5 degrees. Then we took R as a second factor from those two expressions and found out that 2 equals to R. So after we took R from this expression, inside the brackets we left only with 1 over times 30 degrees. And after we took R as a second factor from this expression, inside the brackets we left only with 1 over times 37.5 degrees. So in conclusion, we found out that 2 equals to R times 1 over times 30 degrees plus 1 over times 37.5 degrees. So 2 equals to R and 1 over times 30 degrees equals to 1.732 plus 1 over times 37.5 degrees equals to 1.3032. So in conclusion, we found out that 2 equals to 1.732 plus 1.3032 and 1.732 plus 1.3032 is 3.0352. So in conclusion, we found out that 2 equals to R times 3.0352. We divided this equation by 3.0352 and finally found out that R equals to 2.30352. That is actually 0.6589 units. So in both methods, we found out that the radius R of this circle equals to 0.5689 units. Okay, thank you very much.